So this is a picture from the time I spent here when it snowed. A little different temperature than today. And this is sort of my idea of thinking about the zeta functions of graphs. So you've got various kinds of subjects, and I suppose we could put a whole bunch of other ones in. But anyway, so number theory is in the one branch of the tree, Riemann surfaces, another branch, dynamical systems, and graphs. And then we have the zeta functions down in the roots, the Dedekind zeta function of a number field or extensions of number fields, or curves or algebraic varieties, or finite fields. The Selberg zeta function for a Riemann surface, the Ruel zeta function of a dynamical system, and the Ihara zeta function for graphs. So whatever you know about one of these things, usually you can translate it, although sometimes the translation is a little bit garbled. Sort of like when Google translates something for you on the net. So my graphs have to satisfy what I call the usual hypotheses. So they have to be finite. I'm not allowing infinite graphs with finite bonds or connections or edges. They have to be connected. They're not directed or weighted. So combinatorial graphs. I'm not allowing degree 1 vertices. And the rank of the fundamental group, I think somebody in a talk called that something else. Anyway, it has to be bigger than 1. In other words, the number of edges minus the number of vertices, which is the r minus 1, has to be greater than 0. So here's an example of a bad graph. That guy. It's got rank of the fundamental group is 1. You just have one generating cycle. And it's got degree 1 vertices. I don't like that either. It is connected, though. I guess you can say that for it. And it's very easy to compute the zeta function of it, actually. As we'll see, there's only one prime. Well, two primes, I guess. One going one way. So there's a prime goes that way, and then there's a prime that goes the other way. So it's got, this is an example of a graph with only a finite number of primes, namely 2. That isn't good. You're not going to have a prime number theorem for that graph. So my theorems don't apply. So we would like to label the edges the following way. So you orient them arbitrarily. I'm assuming the graph's not directed. So you direct the edges however you feel like. And then you label them as follows. So on this particular graph, I have used letters, but usually I'm thinking numbers. So E1 I'm going to call A, E2 is B, E6 is F. And then when I do the directions, the opposite direction, E7 is going to be A inverse, that is the edge going the opposite way. E8 is B inverse, going the opposite way. And so on. The 12th one is EF going the opposite way. So this makes some of the calculations easier. I don't know if that'll be obvious in this talk, but anyway. So being a number theorist, I have to find the primes in the graphs. And these are equivalence classes of closed, backtrackless, tailless, primitive paths, which are just a bunch of oriented edges, directed edges, E1, E2, up to whatever. Where S, the number of edges, the number of directed edges is the length. I'm going to call that nu of the path. So the definitions here are the equivalence classes that you don't care where the path starts. So in other words, I'm going to put brackets around C to mean E2 up to ES and then E1. Start with E2 instead of E1. You with me? Similarly, I could start with E3 or whatever. So it's sort of a cyclic permutation of the edges. A backtrack means that EI plus 1 is EI inverse. So that's a backtrack. You're not allowed to do that, just as happened in the first talk. A backscatter, not allowed, illegal. A tail means that you've started, it's really a backtrack if you change the starting point. So in other words, this is a tail. I started the path at alpha, and then I didn't notice that I was backtracking, that the last edge was actually the inverse of the first edge. That's not allowed either because my equivalence class allows me to change the starting point in the thing. I still don't have a prime, so what is a prime? Well, a prime means the path is not primitive. That is, yes. A prime means the path is primitive. Sorry. Not primitive means you go around more than once. You keep going around the same path twice, say. That's not a prime. So and that's the only way not to be a prime. Namely, you go around the same path twice. If you go around one path and then you go around another, go around one cycle in a graph and then you go around another cycle in the graph, you've got a prime there. So we don't have unique factorization into primes, so for number theorists that's disturbing, but anyway. So here's some examples. And again, you get to see the snow. We did have some. We had some great snowmen and things. So for example, primes in this graph, E1, E2, E3, that's certainly a prime. I can also do E4, E5, E3, that's another prime. And I can put them together and get E1, E2, E3, E4, E5, E3. That's also a prime. So basically, if I take the product of two primitive paths, I get another prime. And I can similarly do n times around the first path times the second path, and that's a prime too. So that shows you, as long as the rank's greater than 1, I'm going to have infinitely many primes. And again, the lengths of these paths are 3, 3, and 6. And this is what, n plus 3. So the Ihara zeta function is, as for Riemann, it's a product of over primes. It's really more like the function field zeta functions in that our complex variable appears in a slightly different way from the Riemann. So we're taking u to be the complex variable. We're assuming it's small enough, and which is actually very, very small, and raising it to the length of the prime. That is the number of edges in the prime. Now we have this theorem. I don't know who you want to say it's due to. I call it Ihara's theorem, but if Ihara was looking at the graphs that come from p-adic groups and the Selberg trace formula, so he was always thinking it was a regular graph. And the degree had to be power of a prime plus 1. So he wouldn't look at a 7 regular graph. Oops, sorry. I cannot control my clicker, even though I've had this for 3 years. Okay, so Ihara's theorem says, I think you saw this in the first talk today, that the inverse zeta function is 1 minus u squared to the r minus 1 power, r is the rank of the fundamental group, times the determinant of I minus au plus qu squared, where if the graph's not regular, this matrix Q is a diagonal matrix where the jth entry is the degree of the jth vertex minus 1. So in the regular case, this would be a scalar matrix, because every vertex has the same number of edges coming out. And I think it was called D in the first talk. So D is Q plus 1 in my language. There were a lot of D minus 1s in the first talk. If you call that Q, then simpler. Anyways, so and again, it's sort of a number theory thing because it comes from the p-adic group or q-adic group. Anyway, the zeta is the inverse of a polynomial. The nicer formula, I think, I guess, again, you saw this morning in the first talk, is that if you define the edge matrix W1 to be the 2 times the number of undirected edges, by 2 times the number of undirected edges matrix with ij entry 1 if edge I feeds into edge j in this way, but j is not the inverse of edge I because we don't want to allow backtracking. Then you get this theorem, this much simpler formula, that the inverse zeta is this determinant. The only drawback is that W1 is not a symmetric matrix, whereas before the formula involved only symmetric matrices. So you have to think a little bit more. I think the theorem that you need to understand the matrix W1 it isn't taught in calculus in the U.S. anyway, whereas the theorem you need to understand symmetric matrices is. So basically the Perron-Frobenius theorem, that is the basic fact you need to understand what's going on with this matrix. So this formula says the poles of the Haar zeta are the reciprocals of the eigenvalues of W1, and we're going to call capital R the closest pole to the origin. So that's also the radius of convergence of that infinite product that we had. You could write it out as a Dirichlet series and then use Landau's theorem sort of as an equivalent to the Perron-Frobenius theorem. If you've got a sort of analytic and an algebraic version of what's going on with R. Anyway, so this largest eigenvalue has to be positive real with corresponding eigenvector with positive entries in it. Of course, that's sort of clear in the regular graph case. So anyway, this is the two basic determinant formulas. And then in the Q+1 regular case, that was the one that you heard about in the first talk. For example, there is a Riemann hypothesis that looks a lot like the standard one, and it, at least in the if I were to change variables, which I haven't done in this talk, so my u is sort of a bad variable. So what happens is the Riemann hypothesis says the non-trivial poles are on the circle of radius q to the minus a half and center 0. And that is equivalent to saying the graph is Riemannogen, meaning the non-trivial spectrum of the adjacency matrix is contained in the spectrum of the adjacency operator on the universal cover, the tree. This definition goes back to Lubatsky, Phillips, and Sarnak in 1988, and they produced a huge list of Riemannogen graphs. The moral of this Riemann hypothesis is I should change variables u equals q to the minus s and look at the s variable. But anyways, there's also a functional equation that takes the value at u to the value 1 over qu, where again q is the degree minus 1. And finally I said it, u is q to the minus s. And once you make that change of variables, it looks like Riemann zeta. The functional equation relates the value at s to the value at 1 minus s. So for Q+1 regular graphs, you have a lot of analogs with number theory. If the graphs are irregular, it's not quite so good. Again, in the regular case, the Alon conjecture said that the Riemann hypothesis is approximately true for most regular graphs, but of course it can be false. Any time you write down a graph, you'll see it's false, unless you're trying to make it random in some way. If you look at Joel Friedman's website, you'll find he has a paper, which I think now has appeared in the memoirs of the AMS, saying that a random regular graph is almost Riemannogen, so basically proving this conjecture. And another paper that talks about the irregular graph case, which Harold and I also looked at. We formulated a Riemann hypothesis for the irregular case. It's a little bit more disturbing in some ways than the regular case, partially because there's no functional equation, at least not with the normal change of variables we're going to make. Anyway, I don't want to talk about that so much today. So here's the prime number theorem. It's another thing a number theorist has to have. Again, the graphs have to satisfy the usual hypotheses in order to be able to use the Perron-Frobenius theorem. However, they can be irregular. So I'm now looking at an arbitrary graph, possibly irregular, undirected, unweighted, satisfying my usual hypotheses. So I'm calling the analog of the prime counting function, pi sub x of m, the number of primes, square bracket c, meaning I've taken the equivalence class in x of length m, And then delta, I need that too, and that's the greatest common divisor of the lengths of the primes in X. That turns out to be something that appears in Perron-Frobenius. If you start thinking about what the definitions are, you see why. Then R, again, is the radius of the largest circle of convergence of the zeta function as an infinite product. And then if delta divides M, well, first of all, if delta does not divide M, that pi sub x of M is 0. So this is certainly going to be false. If it does divide M, then this thing is delta times R to the minus M over M as M goes to infinity. If the graph is regular, Q plus 1 regular, R is 1 over Q, it turns out. And so then I'm saying there's lots of primes of length M, namely Q to the M over M. So that's the prime number theorem. It's similar to the one that occurs in counting prime geodesics and Riemann surfaces, compact Riemann surfaces. It comes from, proof comes from explicit formulas for pi sub m of x. I think that was my original title for this talk, that I would look at explicit formulas. So if you ever look at some of the standard analytic number theory books, you'll see there's a huge, for example, who want to prove the prime number theorem. They'll mess around with zeta prime over zeta, the logarithmic derivative of the zeta function, and expand it and play around with that to some extent. The same thing happens in function fields, which is actually closer. The zeta functions of function fields are closer to these graph ones. In fact, they are graph ones in some cases. So anyway, you get a bunch of explicit formulas involving usually n sub m, which is the number of closed paths C in the graph of length m with no backtracks and no tails. I'm not saying equivalence classes here. I'll put square brackets when I'm talking about equivalence classes. So I'm counting paths as different if they start in different places, and also different if they're oriented differently. So it depends on what direction you go around the path. And pi sub x is the number of primes in the graph of length m. So then when you logarithmically differentiate the zeta function, multiply by u, you get the standard n sub m's as your coefficients. And if you think about the zeta functions of algebraic varieties, this sort of formula comes out also, where you're counting points on varieties over finite fields. And similarly with the Ruel zeta function of in some cases. If I want to do a formula with, oops, I pressed the wrong button. If I want to do the formula with pi sub x, I collect the terms in the infinite product for primes of length m, and then I get a similar formula. Over now, what it looks like is the logarithmic derivative is the sum over m, and then a sum over all the positive d dividing m of d times pi of d, and then u to the m. So what that says is that n sub m is the sum over the divisors of m, d pi of d. Sort of a nice number theoretic thing. And you can always invert formulas like that where you're summing over divisors using the Möbius function. So if you want to invert it, you can. From the Ihara theorem, you get this first formula here, that I have a sum. I can rewrite the n sub m as a sum over the eigenvalues of the adjacency matrix A to a power m. Oh, and I didn't tell you what A lambda and B lambda are. Oh, that's bad. They come from, they are the roots of the quadratic that's sitting in there from the Ihara formula, so probably the reciprocal roots. So basically alpha lambda times beta lambda is lambda, and alpha lambda plus beta lambda is giving you the coefficient of u in the quadratic. The second determinant formula is easier. You just get n sub m as the sum over lambda in the spectrum of that edge matrix W1 that measures whether edge E feeds into edge F to the mth power. So if you want to know the prime number theorem, all you need is the Perron-Frobenius theorem to tell you that the largest eigenvalue of W1 is the reciprocal of, it's whatever I said, so I can go backwards, but there it is. So I'm trying to prove this theorem. The largest eigenvalue of W1 is R inverse. So if you put all that together, that's what you get. I have to talk, you need Perron Frobenius. Anyway, the main term here is R to the minus m, and then I have to use this formula to get out what pi of m is. Assuming delta is 1. Delta, of course, might not be 1, and then you've got to think a little harder. So now I'm going to Alaska, which is always good in the summer. Not in the winter so much. So the V-type explicit formulas basically look like this. I'm not going to say too much about it, but you can hope that my version of thinking about this is that these give me an analog of the Selberg trace formula where you can plug in nice functions h and hopefully be able to deduce things like what is if you've got a random bunch of graphs, what's the distribution of the spectrum, knowing stuff about the behavior of the n sub m's, or what's the you would hope to, so I know you can, from the Selberg trace, in the regular case, I know you can use the Selberg trace formula, as was said in the first lecture, to prove the distribution, that you get the semicircle distribution for the eigenvalues of the adjacency matrix. What you would like to do is also get a formula telling you what's the spacing density. Anyway, I don't know how to do that, but that would be what I'd hope to use this formula for. So here you need A is between 0 and R. We're integrating over a circle of radius A. You'd really like A to be 1, which I don't think you can say that, because R is very small. It's 1 over Q if you have a Q plus 1 regular graph. If you let H of U is U to the minus n minus 1, then you get one of our earlier formulas. It's not so interesting because we already know it. So anyway, that's the story of n sub m and pi of n. And here's an example. If you do this logarithmic derivative of the complete graph on 4 vertices minus 1 edge, you get these n sub m's. So there are 12 paths of length 3, 8 paths of length 4, where we're counting where the path starts. If it starts in a different place, it's a different path. And we're also counting orientation. So because we know n sub 3 is the sum of all the divisors of 3, d times pi of d, what this tells us is pi of, and there's only 2 divisors of 3, right? 1 and 3. So this and I know that pi of 1 is 0. There's no prime of length 1 because they would have to have backtracking. So this tells me that 12 over 3 is pi of 3, yeah? Namely 4. And you can see them, right? So there's that prime, there's that prime, and then there's the same primes in the opposite direction. So there's two visible primes of length 3, right? And then the same ones in the opposite direction, so that gets 4. Pi of 4, same story, pretty easy to see why there's 2 of length 4, right? You just see 1 prime of length 4 and the one going in the opposite direction. 5, there's nothing of length 5. 6, well, you got to think a little harder. You got to use this formula to see how I got there's only 2 of length 6. Although I guess you could probably see it if you look at it long enough. So anyway, the explicit formulas can be used to answer really explicit sort of number theory questions, if you like, about what the pi's are. Okay, so now I want to talk about a slightly more complicated number theory questions where you're thinking that we have a graph covering, and that's an analog of extensions of number fields. So to do those kinds of questions, you need to look at Artinel functions of graphs. Again, we're in Alaska. Ooh, the humpback whales. Okay, so I'm going to talk about graph Gawa theory. which you could do for Riemann surfaces or any kind of differentiable manifolds covering each other, or topological guys covering each other, spaces. So the idea is we're going to look at Y, an unramified covering of X, to mean if I have no loops or multiple edges, that we have a projection pi that is an onto graph map that has the property that for everything down below in X, I'm thinking of X as the base graph and Y is up above it. For every point in the inverse image under pi, the map is 1-to-1 onto for everything adjacent to Y. So that is locally, if you just look at a point and its neighbors, a point and the point above and its neighbors look the same. A normal D-sheeted covering means we have D graph isomorphisms preserving pi, our projection, and our Galois group, like so. So for example, how do you do this? Well, you pick, so here's my graph X, the base graph, down below, and I pick a spanning tree in X. So you've got to imagine that this isn't all of X. There's still other edges that I haven't drawn in yet. And then you make D copies of that tree, however big you want your covering to be. I'm beeping. Technology and I never get along. Especially microphones. Anyway, so if we ignore those dots there, suppose we have 3 copies. We want a 3-sheeted covering. Now we're going to think the Galois group acts on the covering in a simple-minded way. So I'm going to label the vertices down below with alphas with Greek letters, and in the covering I'm going to label the vertices with group alpha and group elements. So I'm imagining that the G acts on the sheet of the covering to give me the sheet GH. So if H is a sheet, G acts on it to give me the sheet GH, and G acts on alpha H to give me alpha GH. And then G of a path that goes from alpha H to beta J in the covering will be the path from alpha GH to beta GJ. And so what happens is, if you're given a group G, you can get examples if you have a permutation representation of the group. And it will tell you, say, if you have generators associated to the edges left out of your spanning tree. So here's an edge left out of the spanning tree of the base graph. Then once I have the permutation representation, let me forget about those dots. So let's say I have 3 covers. So this would be the permutation 1, 2. And then if I also know it's 2, 3, then that's how I lift the edge. And so given the right situation, you can make up all kinds of examples. And I'll show you a few. You can't do everything you might want. Some things are impossible, but at least for unramified. So simplest example in every book on graph theory that talks about coverings anyway, so for example Biggs, the cube is a covering of the tetrahedron. That is, this is the complete graph on 4 vertices, that's the tetrahedron. It's a covering because if I take this spanning tree here in red, then if you make 2 of them, you get the covering. You see, I've got 2 spanning trees in red up above, or to the left, more or less. And then when I lift the edges left out, what I always do is go from one sheet to the other sheet, and that gives you the cube. Now you could also imagine doing something slightly different, then you would get a different thing from the cube. So here's my evil exercise. State and prove the fundamental theorems of Galois theory for this situation. The answer more or less is in this book, which should appear by September, unless, oh wow, Cuba. There's a good typo. And it will be full of typos. But Cambridge University Press proof copy editor said I couldn't say in the introduction, this book is full of typos. I suppose that was wise, because they're probably going to charge a fortune for it. Anyway, it will be. So, before you try to do the evil exercise, you have to make a whole bunch of definitions, because you can get in trouble very easily. And one of the definitions is what you mean by an intermediate cover. So I have this big covering y over x. What's intermediate will be a z, such that pi 2, when I compose pi 1 with pi 2, I get pi, the projection all the way down to x. That's all you mean by intermediate. Where all these, of course, are graph maps. They preserve incidence. They preserve adjacency, sorry. All of the pi's must preserve adjacency, and of course they're onto. And they have the property that the inverse image of every point is, what I said. Locally, they're local isomorphisms. So, and then you have to define what you mean by when are two intermediate coverings equal. And so you first do covering isomorphic, meaning that z and z prime are covering isomorphic if there's a graph isomorphism from z to z prime that preserves this triangle here. So in other words, I composed with pi 2 is equal to pi 2 prime. And you have to say that not only that, but the lower triangle gets preserved by the isomorphism to call z equal to z prime. And then really you can get from one thing to the other by the correct renumbering. This is really all Harold's definitions. I don't know what I would have said, but I would have been like totally wrong. If you don't make these definitions, you can't do the exercise, the evil exercise. So you get the fundamental theorems of Galois theory, as you might expect. If you have an unramified normal cover with Galois group G, there's a one-to-one correspondence between subgroups of G and graphs, which we're calling Z of H, intermediate to y over x. And each intermediate graph corresponds to a subgroup, H of Z, and you can have all the usual properties, namely if you have a couple of these and the subgroup HI corresponds to the ZI, then Z1 is intermediate to y over Z2 if and only if H1 is contained in H2. There's sort of a flip between the inclusions, if you like, as it would be in the classical case. And then what you can discover is that two intermediate graphs are covering isomorphic if and only if the corresponding subgroups are conjugate. And if you want to talk about normal subgroups, then what do you need? So Z is an intermediate covering to y over x, then Z is itself a normal cover if and only if the corresponding, in other words, a Galois cover, corresponding subgroup is a normal subgroup. And then the Galois group of Z over x is the quotient group. So the standard facts about Galois theory are all true with some effort. And you can also do what number theorists like to do, which is talk about what happens to primes in coverings. So I'm going to look at a prime in my complete graph on 4 vertices. And then the question is, what happens when I lift it to the cube? Well, so I'm going to start at A double prime, meaning the second sheet of the cover. This goes from A to D, so I have to go from A double prime to a D. There's only one to go to, and that's D prime. And then from D prime, I have to go to C. So I have to go up to C double prime. Then I have to go from C to A, so then I go to A prime. There's only one way to do this lifting. But I'm at A prime, not A double prime, so this is not a prime. I've lifted a prime, but I've got something that is enclosed, so it's not a prime. So I've got to keep lifting, and if I want to see what is the prime above, so I lift again, and now I'm back to A prime. So I had to lift twice to come up with a closed path. So that's what we call F equals 2. In classical number theory lingo, you have three things, E, F, and G. E is 1 and because we're never going to have ramification because we don't know what to think about. G is the number of primes above. There's only one. So this is a picture of a prime which is called inert. That is, F is 2, G is 1, E is 1. It's too bad I don't have time to do a number 3 example, but anyway. That's the situation. It turns out these F's and G's behave exactly as they do in number 3. So I have 1 prime above, and it's a lift of c squared. So that tells me F is 2. Second example, the G is 2 case. So here's a prime of length 4. When I lift it in the same way, oops, I'm doing the wrong thing, I actually get a prime. I only have to lift once, I get a prime. But there's another one. If I started at the other A on the other sheet, I would get the second prime. That's the case. There's 2 primes above. That's G is 2. This is a picture of splitting completely. What number theory is called splitting completely in a quadratic extension. There's 2 prime ideals above, and the residual degree, the degree of the finite field extensions corresponding is actually 1. And you only have to lift once in our case. So let me talk about the Frobenius automorphism for graphs. Some graph theory books they have another name for this, but I can't remember what it is at the moment. So again, I've got a prime below some graph x. I've only drawn the prime, and I lift it once, and I get this thing. So I start on sheet I, end on sheet j. I have a unique lift starting at sheet I, ending in sheet j, with the same number of edges in it. It may not be a closed path. So then we define the normalized Frobenius, sigma of c, to be the sheet you end on when you start on sheet 1. So that is if I equals the identity element of our group, that'll be sheet 1. In general, of course, as we saw, different things happen. So if you start on some other sheet I, then the Frobenius is going to be called Ji inverse. So it's the map that takes sheet I, the initial sheet, to the terminal sheet j, with one lift, which is unique, once you tell the starting sheet. So the exercise here, which isn't evil, is to compute the sigma from the preceding slide. Can you do it? So what was the sigma of the last slide? This is the pop quiz. What's the sigma here? I basically start on sheet 2. Well, if I start on sheet 1, I end on sheet 1. Yeah? So sigma is the identity. Sigma of G is the identity in this case. That's the splitting completely case. And the other one, you got the other element of the Galois group. So I get 1, the trivial element of the Galois group for that one. Here's a more interesting example where I've got a non-normal cubic cover. That's this guy, and I've taken one edge off the complete graph with 4 vertices. It's Galois. This is not a Galois cover, but it sits in a Galois cover, which has got Galois group S3. So it's a lot more interesting to test things on. See what I said about it. Well, we'll talk. Yeah. So for example, if I want a prime that splits completely in the non-normal cubic, it turns out it has to have length 10. It takes a while to figure out what prime will do that, because primes of length 10 are fairly complicated. So my question to you is 10 the smallest length of a prime that splits completely, namely that has f equals 1 and g equals 3 in this non-normal case even? It also splits completely in the full S3 6-sheeted cover. And this basically comes from the Chebotarev density theorem, which I've got 5 minutes to get to. Oh, good luck on that. So anyway, the Frobenius has all these standard properties that it's it's only determined up to conjugacy by the upper prime. If you change sheets of the cover that you start on, then you're going to conjugate the Frobenius. If you vary the starting point, though, nothing happens, so it's really independent of our equivalence classes. It's also a group homomorphism, if you like. A Frobenius of AB is Frobenius of A times Frobenius of B. So you can define the art and L function exactly the same way you do in number theory, except that it's easier because we don't have any ramification. So I'm just taking the product over primes of the base graph X. I take a representation of the Gawa group, a complex number, has to be small to converge. I take rho of the Frobenius of a prime above, and again, this depends on the, it's not defined except up to conjugation, but unless I use normalized Frobenius. That doesn't matter because I'm taking a determinant. And Frobenius is a homomorphism, and so is a group representation. So conjugates come out. So it looks just like the ordinary Ihara zeta function, except it has now a group representation stuck in. So in particular, you see that that is a very scary. That if the representation sends everything to 1, then you get the original Ihara zeta function. Also, this other basic property that explains factorization of all these zeta functions, namely that if you take a product over all irreducible representations of the group, everything taken degree number of times, you find the Ihara zeta function of the top graph in the covering, assuming, of course, it's normal covering. And you have this determinant formula that's pretty simple to write down, namely I take the representation at sigma of an edge E, the first edge, times the entries of the ordinary W1 matrix. You get the same sort of determinant formula you had before. There's also an Ihara formula with the same sort of proof. More Alaska. And so you can easily compute the zeta functions of the cube and the tetrahedron. And then you get all kinds of explicit formulas. I don't have much time, so perhaps Tom will show you some more of these. If you want to count the number of closed, no backtracking, no tail paths of length m whose normalized Frobenius automorphism is a given group element sigma, all you got to do is take the logarithmic derivative. Oh, there's no L there. Of the L function at u rho y over x. There should be an L between the log and the parentheses. And then the coefficients have sum over Gawa group and the character chi rho of the representation. That is the trace of the representation rho. And then if you want an analog of pi, you have a similar formula with sum of divisors of m. And again, of course, because of the determinant formula, you can change this to a sum over the spectrum of the W1 row matrix. And so if you put all that junk together, plus this trick that if you don't like the sum over G, you can get rid of it and replace it with the sum over representations rho, a trick that goes back to Dirichlet, I guess, in number theory, using the dual orthogonality relations between the characters of the representations. Then you get this sort of formula, where if I sum the complex conjugate of the character times the L function, the logarithmic derivative of the L function, I get this. So now I've gotten rid of the sum over group elements S and isolated out the n sub m of S. And similarly, that, of course, gives me a formula involving the spectrum of the W1 row matrix. And so you put this together and you get the Cherev-Taref density theorem, which says that basically the analytic density, which is this thing, so it's the limit as u goes to the that first pole from below, the sum over the things in a set S, u to the nu of c, that is the length of the primes, the sum over all primes, what you get is that density, assuming the graph satisfied the usual hypotheses, y over x is normal, G is a fixed conjugacy class in the Galois group, is the density of primes such that the normalized Frobenius of the prime is this fixed, the class of the normalized Frobenius is the fixed conjugacy class, is the order of the conjugacy class over the order of the group. So what that tells you in particular is if you're looking for the primes that split completely, as I was looking for before in the talk, the prime of minimal length that splits completely in that 6th degree extension or covering, then I take G to be the identity. So this thing would be a 1/6. So the story would be 1/6 of the primes down below split completely in that big extension up to the full 6-sheeted cover. So that says there are few of them because most of the primes have a bigger conjugacy class in the symmetric group, right? Because usually you'll have either 2 things or 3 things. Only the identity has 1 thing. So this gives you some clue why you had to go up to length 10 in that case. I think I won't show you this picture. You can actually work out this example in more detail and talk about why it's 10 by computing the logarithmic derivatives of all the L functions, adding them up, seeing you get only terms with u6 and u10, and so the only possibility would be that there's a prime of length 6 that splits completely, and the fact is that there isn't. The paths of length 6 that lift to closed paths are from squares of primes, and that makes them not prime. That's the only way not to be a prime, not to be a power of a prime. So that's the answer to my question, and I will stop. And here's some references. The end.